Hello everyone, here we are with the second session of the drug stability, and in this chapter we will going to discuss about the several factors that are physical and chemical factor which can influence the chemical degradation of the pharmaceutical product. So the most common factor which can affect or influence the rate of degradation of any of the pharmaceutical formulations are the temperature, solvent, its ionic strength, dielectric constant, and specific and general acid base catalysis. So here we will discuss it one by one. Firstly, the effect of temperature on the chemical degradation of the pharmaceutical dosage forms. Higher is the temperature, greater is the rate of oxidation or reduction and hydrolysis reaction, which can lead to a higher rate of degradation. So we can say that if we increases the temperature, then it can accelerate the oxidation, reduction and hydrolysis type of reaction, which can accelerates the rate of degradation also. So basically we have three types of temperature. The temperatures are room temperature, cold or refrigerated storage temperature, and lastly we have freeze temperature. These are the temperature at which the pharmaceutical product has been kept. So firstly, room temperature, it lies in between 25 to 30 degrees Celsius. Then we have cold temperature or refrigerator temperature. It lies in between 2 to 8 degrees Celsius. And then we have freeze storage, which lies at a temperature range of -20 to -10 degrees Celsius. Generally, the speed of many reaction can be increased 2 to 3 times with each increase of 10 degrees Celsius in temperature. It means that if we increases the temperature by 10 degrees Celsius, then the rate of degradation of reaction can be increased by 2 times or 3 times. The effect of temperature can be given by Arrhenius equation, which is K is equals to AE to the power minus EA by RT, where K is the kinetic rate constant at time T, EA is the activation energy, R is the energy rate constant, T is the Kelvin temperature, and capital A denotes the collision frequency factor, which is completely dependent on the structure of the molecules. So from this equation, if we have higher rate of temperature, then there will be a greater value of rate constant, and it results in the greater rate of degradation also. If we have a higher activation energy, in that case also the rate constant value is greater, and it will also result in a higher rate of degradation. If we have similar type of activation energy, or we can say that if we have lower temperature or lower activation energy, then small is the rate constant, and hence the decreased rate of degradation can be achieved. Now we move on to our next factor, that is effect of solvent. The effect of solvent on the rate of decomposition of drug is related to the relative solubility of the reactant and the product in the given solvent. The rate of decomposition reaction depends on the nature of the solvent, that is polar or non-polar in nature. It is found that the nature of the solvent affect rate of decomposition or degradation. It means whether the solvent is polar or non-polar, it will directly going to affect the rate of decomposition. Some of the observations are that if the polarity of the product is similar to the polarity of the solvent, I repeat, if the polarity of the product is similar to the polarity of the solvent, the rate of reaction will be large or it will be positive in nature. But if the polarity of the reactant is similar to that of the solvent, the rate of reaction will be small or negative. Hence, polar solvents generally increases or accelerates the reaction that form product having higher polarity than the reactants. In contrast, if the reactants are more polar than the product, such reactions are accelerated by polar solvent and retarded by high polar solvents. Next effect is of ionic strength. An increase in ionic strength of solution would tend to decrease the rate of reaction involving interaction between oppositely charged ions and increase the rate of reaction between similarly charged ions. The rate of reaction is affected by the ionic strength of the solution according to the following equation, where log K is equals to log K naught plus 1.02 ZA ZB under root U, where ZA and ZB are the charges carried by reacting species. Use the ionic strength, and K is the rate constant of degradation. K naught is the rate constant at infinite dilutions. For example, if you add a salt in any of the liquid formulation, it means there is an increase in the ionic strength due to the dissociation of that particular salt. For example, if we take NaCl, NaCl when added into a solution, it gets dissociated into sodium ions and chloride ions. So these ions may increase or decrease or have no effect on the degradation of the drug in solution. So when we plot a graph in between the rate constant and the ionic strength, it gives the effect of ionic strength on the rate of degradation. The concentration of the salt which we have added into the liquid formulation, it may either increases or decreases or have no effect on degradation of drug in solution. When the drug is positively charged and the rate of reaction is catalyzed by hydrogen ions, increase in ionic strength due to addition of any of the salt like NaCl increases the rate of degradation also. These effects get reversed if the drug is positive in nature and the reaction is catalyzed by hydroxyl ions. In particular case, if a drug is neutral in nature, then there is no effect on degradation rate. So charge on the drug is basically responsible for any increase or decrease or having no effect on the rate of degradation of the reaction. Here in this graph, you can see that the first line is representing the positive type of charges. The second line, which is constant linear line, representing a neutral type of drug. And lastly, we have a drug which is having a negative charge on its surface. Now the effect of dielectric constant. So firstly, we have to know about dielectric constant. What is it? Dielectric constant is basically the measurement of the polarity of a solvent. The higher is the dielectric constant of a solvent, more polar it is. For example, the dielectric constant of water is higher than that of methanol, as water is more polar than the methanol. Reactions involving ion of opposite charges, an increase in dielectric constant of solvent results in decrease in rate constant or in the rate of reaction. Reaction involving ions of like charges, an increase in dielectric constant of solvent results in the decrease in rate constant or in rate of reaction. The reaction between neutral molecules which produce a highly polar transition state are also enhanced by high dielectric constant solvent. Here, dipole molecule can also be known as neutral molecule or vice versa, which have no charges on its surface. In that case, if we increase the dielectric constant, then the rate of reaction will be decreased, and decrease in dielectric constant will result in the increase of the rate of degradation. So the next factor, we move on to specific acid-base catalysis, or we can simply say the effect of pH on the rate of degradation. The reactions which are dependent on hydrogen ion concentration or hydroxyl ion concentration are known to be subjected to specific acid-base catalysis. Hydrogen ion catalysis is predominant at lower pH, while hydroxyl ion catalysis operates at a higher pH, because we know that there is a higher concentration of hydrogen ion at lower pH. At intermediate pH range, the rate is dependent on pH or catalyzed by both the hydrogen ion or the hydroxyl ion. Effect of pH on degradation rate can be easily measured by determining decomposition at different pH. So for this, we have to prepare the different pH solution of the drug, and determination of the concentration at different pH solution has been done. We'll come to know by this that how much degradation occur at different pH. Finally, a graph is plotted in between the log of rate constant, that is K value, and the pH to find out the optimum stability. The optimum stability is basically the pH at which the decomposition or the value of K is the lowest. If the value of K is lower, the rate of degradation is also lower. The inflection in this particular graph represents the optimized stability. As in this graph, the pH around 3 has an inflection and it represents the optimum stability. Now we move on to our last factor, that is general acid-base catalysis. If the decomposition is affected by different concentration of the buffer, the reaction is called general acid-based catalyzed type of reaction. We all know that buffer are generally added to maintain the pH, but it was found that buffer may also catalyze the degradation of the reactions. They may also be responsible for the degradation of reaction in solution form. Buffers are added to maintain pH, as we all know. So when we move on to this graph is particularly representing the effect of citrate buffer on cefadroxil, that is an antibiotic type of drug. So decomposition constant, that is K value, is represented by y-axis, and the molar concentration of citrate buffer is represented on x-axis. Here you can see that at different pH there is different rate of degradation. For lower value of molar concentration, the K value, that is the rate constant value, is less. Hence the degradation is also less. As the molar concentration of the citrate buffer increases, the K value also increases, and ultimately the rate of degradation also increases. Here in this graph, it is clearly showing that at higher pH, that is at a pH of 5.82, higher rate of degradation occurs. So higher is the value of pH, greater is the rate constant, and greater will be the rate of degradation. Lower is the value of pH, as it is represented here by pH 2.51. Lower is the value of rate constant, and lower is the rate of degradation. So these are some factors by which we can easily determine the degradation of reaction which has been done chemically. So this is all for about the physical and chemical degradation factors which influences the rate of degradation. Thank you all.